Okay. All right, very good. Yeah, so I have the honor today of being here and trying to tell you something about my research. And as Rohini and Mishra ma'am both said, it's a rather fortunate occasion because we have basically kind of three generation of particle physicists who are here in the meeting at this time, and we all have a very good connection with each other, and such kind of formation of bond is something quite nice and quite rare, actually, according to me. And it's very nice to preserve that and be here at this moment. So with that, let me actually start with a little bit of reminiscence, so to say, about my memories of being at UDP. And the first memory that comes to my mind is actually a day almost 15 years ago. I particularly remember this day because when I finished my bachelor's and I was going to start my master's, I actually wanted to very much get into area of astrophysics and astronomy. I was very passionate about it. And I didn't have admission for astrophysics specialization at the time. So I went to the university. And I remember very much for the first time, you know, going into the office of Mishra and said, I'm admitted into this nuclear physics specialization, and I really want to do astrophysics. And I don't know what to do about it now because I know nothing about nothing. And at the time, ma'am said, you know, you should give it a try. It's not, it's a very exciting area and you will learn a lot, and I'm sure you will enjoy a lot. And I took that advice and I went through with the admission, and really that particular day and that particular advice changed my life because today I'm doing particle physics every day and I couldn't be enjoying it more. So one of the lessons that I learned from that day, which I today try to keep in my mind, is always keep an open mind. Opportunities come your way. Take what is presented to you and make the best of it, because that's one of the things that will always pay off in longer term, right? So I did my master's at the department during 2004 and 2006. And I have very, very fond memories because not only we had great lectures, but in particular, we had great mentoring. And this is very important. I remember, you know, discussing many hours or many questions with Mishra ma'am, with Press sir, with Natarajan ma'am, Patel sir. We had very nice interactions also with Kothari sir and Gupta sir and Dubey sir and all other people who are at the department, and I forget many names at this point. But essentially, I remember just taking time from all the professors all the time because I wanted to ask questions, and they devoted that time to me to answer the questions, to give me books, to give me directions. And this was very useful. And today I know that doing that kind of thing, doing that kind of mentoring is extremely time consuming. And giving time to students is one of the most expensive things that the professors can do. So I'm very grateful that I had this opportunity to be able to take time from my professors and my, you know, my mentors at the time. And apart from this, I also had, because, you know, I always pestered everybody, I had a lot of also opportunities to attend summer schools. So I still remember Mishra ma'am, when she came and she said, well, do you want to go to Chennai and do a summer school with somebody there? And I said, yes, I will. And it was all arranged at the very last moment. And I went there. I worked with Rahul Basu and learned a little bit of quantum field theory. It was fantastic. And Patel sir sent me to Inter-University Accelerator Center in Delhi. And then I attended also the ACRC series where I think I met Rohini for the first time and all these kinds of things. It was basically possible because I had professors who were dedicated to getting students somewhere. And this was very, very relevant. So I really want to thank the department for that, for just having these people who thought the best of the students, right? And this is something I try to do, and I will continue to do so as long as I can. The other very important point that I want to mention is I had the pleasure of having very strong female role models. And this was very relevant because um, it gives you the possibility of achieving the dream. If I have examples who could do things, there was Mishra ma'am, there was Bhattacharya ma'am, there was Natarajan ma'am, so many female professors who were around. Later on, I met Rohini. And all this basically inspired me that, okay, I could, in principle, take up the career of being a researcher and do something out of it. So on one hand, I had these high-level professors and dreams that I wanted to achieve. And these were very nicely complemented with colleagues and friends with whom I could discuss. And I still remember, like every day in the library, we had a huge desk which was dedicated to students from MSc of our batch, and we would sit on that desk. The books were littered all over the place, and then all of us would discuss and take notes, and just work together. We never left library before the library closed down. So we were there right after the end of the lectures until the end of until the library closed down. And to date, I remember the desk. Even if I go there today, I know exactly where we used to sit all together. This was fantastic. And then, of course, there are many, many random memories. And I remember the lecture hall complex where you could get instant coffee and attend lectures. There were also very nice discussions and very beautiful friendships formed with students from other departments. And one of my favorites was psychology department, and I could have a lot of discussions there. Not to mention, we are talking about Mumbai, and I didn't live on the hostel. So I spent many, many hours on crowded trains and buses, and also formed a lot of clubs and friendships on these commutes. And I think it's part and parcel of being a Mumbaiker, which is you form friendships and relationships no matter how you go and how your life evolves. And some of these are basically lifetime relationships and lifetime friendships. So after my PhD, I spent some time searching for a PhD position. And one of the things that I tried to do at least is to keep on learning new things during this time. So not to just sit at home or not to just keep appearing for exams, but keep learning new things, keep doing new projects so that I have a continuous evolution and progress every second or every next day. So I wanted to learn something more every day, and this is something I tried to do. Fortunately, it all paid off, and I got a PhD position in Germany, and I came to Europe now a bit more than 10 years ago. And as Mishra ma'am was saying, I did my PhD in Germany, and then I went to Grenoble in France, and then I'm here in Vienna. I almost forgot. I do see that a lot of people who were actually together with me are also logged in today. So I do remember Ajay sir. I still, if I call Mishra ma'am, and I would call Ajay sir, because that's how I got introduced to all of these people at the time, and it keeps in the habit, I guess. So I remember Neelam, I remember Swati, Ajay sir, all these people, and these were very fond times, which I still remember today. So one of the things I did want to flash quickly was actually I still to date have the particle physics lecture notes that Mishra ma'am taught me, right? So I think I also have lecture notes from other courses of hers, but I do remember these lectures. Every time I see these notes, I have so many nice memories, and I still learn to date a lot from what we discussed almost 15 years ago now. So it's really a resource, a treasure that stays with you for a lifetime. Okay, very well. So with this, really having had this pleasure of being taught by some of the very dedicated people that I could see on the planet, I went on to basically connect my dream of being in astrophysics with my passion of learning about particle physics. And one area where I could pick up was the question of dark matter. And I'll tell you a little bit about what this problem is and why do we sort of believe in the efforts that we are making today. I will not go a lot in technicalities, but I'll try to give you a flavor of how things are being done today. Uh, by my specialization, I do a lot more on particle physics side than astrophysics side. It's, I would like to do a bit more astrophysics, but there's only so much time. Uh, Nevertheless, I'll sort of try to cover very different aspects of the problem of dark matter and why, from the point of view of particle physics or from the point of view of just being curious human beings, we should try to understand this mystery. So the idea is to talk a little bit about what is the evidence of dark matter. So why do we think it exists? How do we search for it? And what have we learned by basically understanding connections between theory and the experiment? So the searches and the concepts, right? And then I'll sort of try to briefly flash some of the future directions that the field of dark matter can take. For what will follow, I will assume that dark matter has an explanation in the language of particle physics. That is, it is made up of particles, right? It's an assumption at best, but it is a very good assumption. And it is good to assume so, because the standard model of particle physics, the elementary stuff that you and me, we all are made up of, we know is incomplete. And we know it is incomplete because it does not explain gravity. Gravity is not a part of standard model. It's a thing on its own. We understand it, but it's not a part of a fundamental theory of high energy physics, so to say. It doesn't explain something called dark energy, which also exists in abundance in the universe. And to date, we haven't had a very good explanation of what it could be. We know that neutrinos have masses, but again, within the standard model, the neutrinos are massless. We don't know what generates the masses of the neutrinos. And also within the standard model, we don't know how matter and antimatter symmetry was generated. You know that every particle has its antiparticle. And if particle and antiparticle were in equal number, everything would have annihilated by now, which means you and me shouldn't have been here. But the very fact that we are here tells us that there is a lot more matter than antimatter in the universe. So where has all the antimatter gone and how has it gone away is a big question to which standard model at the moment doesn't have an answer. It doesn't explain also things like inflation, and it doesn't explain, for example, why the mass of the Higgs is protected from quadratic divergences. So there are a number of problems with standard model, and then you would say, well, if all these problems already do exist, probably dark matter is also a part of this list. So, and therefore, it becomes very well motivated that dark matter is also expected to be a particle. And you would sort of want to examine whether such kind of assumption or well-defined or well-assumed motivated assumption takes us somewhere or not. So a little bit of dark matter trivia is it's everywhere, okay? Dark matter exists, as I will show you briefly in a couple of slides, it exists everywhere. It's not a specific place in the universe, it's all throughout, and we know because we have observed it. It's about 5 times more abundant than ordinary matter, right? So if you think that there is in terms of things that you and me are made up of, it's a lot, there is 5 times more matter in the universe that we don't know at the moment about, okay? So how do we know this? We know this because we see that there is a strong evidence of dark matter from the scale of galaxies to the scale of observation of the universe. Okay, so here you see on the top box on the slide, where you have basically all different scales at which we have seen dark matter. And I'll sort of walk you through these scales to tell you what the evidences are. So one of the first evidences is at the scale of galaxies. You can measure the velocity of the stars, as you see here on the bottom left of the slide, where if you calculate according to the Newton's law of gravitation, you essentially would see that, or assume that the velocity of the stars falls as it goes away from the center of the galaxy. But as you see on the plot here, the velocity remains approximately constant. So why would it be constant if there is no dark matter? Has no good reason. And you could explain these rotational curves basically if you assume that there is a dark matter halo in the universe, right? And this is actually a rather straightforward calculation to do, as I show on the slide. You essentially have to compute the velocity. So you can compute the velocity of the dark matter, of the velocity as a distance of function of the distance, by equating the Newton's law with basically virial potential. And what you get here is, as I show in the box below, that the velocity of such dark matter particle is about 200 kilometers per second, okay? So one of the things that you know is basically that dark matter travels very slow. It can explain the rotational curve of the galaxy, and the velocity is about 200 kilometers per second. This is a number you can derive. There is nothing magical about this number, okay? You can also then go to the scale of clusters of galaxies. So what you see here on the slide is a picture from Coma cluster, which is one of the very well-studied object in terms of dark matter evidences. And basically, Zwicky did one of these first calculations where he tried to compute what is the kinetic energy versus the potential energy of this particular cluster. He did it via various different methods. And if you can lay your hands on this paper, I would actually encourage you to read this paper. It's a very beautiful paper. And with the help of very simple calculations, he shows you how you can come up with the fact that there has to be a lot more invisible matter at the scale of cluster compared to the visible matter, okay? And this was basically also another evidence for basically why we expect dark matter to exist, because you can weigh the clusters using light, or you can weigh the cluster using gravity, and these two things don't match unless you add an invisible component to the entire story. Throughout my talk, I will also try to give you several archive articles, which are very beautiful to read in itself. So here is, for example, a very nice read on the history of dark matter, and basically how people came up with a ton of evidence which convinces us that this thing exists in the universe today. Okay, so we can move on and we can ask, do we see dark matter at the observable scale of the universe? And in fact, we do, right? This is one of the most precise measurements of the amount of dark matter that exists today. So what you have here, for example, on the bottom right of the slide, is basically what is called as the CMB measurements. So CMB was basically the last light that you see before the universe became again opaque. And you can measure these CMB peaks, as you see here again on the bottom left of the slide. And the ratio of the first peak to the second peak basically tells you how much of dark matter exists in the universe, okay? And we had a ton of satellites which went up there and measured these peaks very precisely. It was one of the, to date, I find it highly exciting that we did that, but we did. And today we know from these measurements that about 25% of all the energy density of the universe is contained in dark matter. The other about 70% is in dark energy, and ordinary matter, standard model particles, things that you and me are made of, is hardly 5%. So we do all the business, we try to measure so many properties, and all these things go down to explaining just 5% of the universe. The fact that to date, we don't have a complete idea of what are the fundamental laws that governs 95% of the universe should excite everybody. I think that's an amazing fact, right? So we've gone and we've done simulations of it. Okay, we've basically put dark matter particles in gravitational potentials, let them evolve, and see how the universe looks like. And these simulations have been incredibly successful. And one of the simulations that I'm showing here comes from the so-called Via Lactea 2 simulation. So basically, these simulations look at the scale of the galaxy, not the scale of the universe, not the scale of CMB that I was talking about, but really galactic scales, still a little bit bigger. And what you see here, at the center, you see that there are bright spots, and this bright spot corresponds to the high density of dark matter, okay? And then as you go away, the density of the dark matter falls, and you also see that there is a lot of smaller dense spots, and these are basically subhalos, or what are called as subhalos in terms of dark matter nomenclature, right? And this is something that we kind of see, and also in the universe when we observe. So it's incredibly nice that when you put dark matter particles in gravitational potential, what you get out of it is a reasonably good picture of the big universe that we see in front of us. That tells us that we are not completely wrong in thinking about this whole story, okay? Most likely. So because you have the simulation, you have data. And using this data, you can basically write down how the density of the dark matter evolves from large distances to small distances, okay? These are parameterizations at this moment. So here you see on the right-hand side, you have the plot, which basically tells you the density of the dark matter as the function of the distance. As the distance increases, you go further and further away from the center, and the density falls. If you go towards the center of the galaxy, the density rises. And this fits very well with the simulation. If you add baryons, which is standard model stuff, basically, this behavior changes a little bit, and this can also be basically modeled, as you see on the plot. But there is a caveat, and the caveat is that this doesn't perfectly match the reality. So this, the blue line or the black line, which are preferred by simulations, as I showed you on the last slide, are not the complete description of reality as we know from dark matter today. And I'll come back to this point towards the end of this talk, okay? So we have a collection of dark matter particles in the universe. They all are moving around with an average speed of 200 kilometers per second. That's what we have seen so far. But since it's a collection, of course, there is a distribution of these velocities. So we have the simulation, and we can look at the velocity distribution of dark matter from these simulations. And what you see on this slide again is the velocity distribution of dark matter as a function of, basically the distribution of dark matter as a function of the velocity. It peaks nicely at around 200 kilometers per second, as we were expecting. And theoretically, we've modeled it as a Maxwell-Boltzmann distribution, okay? This is something you all have seen in your thermodynamics courses. Except the fact that if you look at the fit from the simulation, it fits reasonably well, but not exactly. And it becomes even more interesting because if you go and actually try to from observation, extract this velocity distribution of dark matter, it at times it deviates even further. Okay, so that tells you that again we've got the big picture right. On an average, dark matter moves at the velocity of 200 kilometers per second. But when it comes to how they are moving or what is the distribution of their velocities, we haven't quite gotten it right. Okay, so there are mysteries which are sort of going around in this picture. Okay, so that tells you that we have good evidence of dark matter going from galaxies to the observational scale. Simulations get the big picture right, not the details, but the big picture. And that tells us a few properties of dark matter that we can infer, okay? So one of the things we know about dark matter is that it is charge and color neutral. And every statement that I'm showing on this slide here has a caveat. So I'm going to tell you the statement and I'm also going to reverse it and tell you what it can also be, okay? So dark matter needs to be charge and color neutral, or it has to be milli-charged, means it can have fractional charges, okay? It can couple very, 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 very weakly to the photon. It does not couple to light, or it couples extremely weakly to the light. It has to be non-relativistic. That is, most of it has to travel slow, but a small fraction of it can still travel fast, okay? It has to have a lifetime which is greater than the age of the universe, or it needs to be stable, which means that dark matter can decay so long as it decays at a lifetime greater than the age of the universe. It has to live very, 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 very long. And then if it can decay, it's fine, okay? It has to have weak interaction with standard models. This is something we know from a lot of experiments today, that it has to have weak interactions with standard model, which in turn means that it can strongly interact with itself. Nobody has excluded that possibility so far. It needs to have mass, which means it needs to have mass greater than 0, but it can be very light. Nobody has stopped a dark matter being a very light particle. Okay, so these are kind of, again, big picture conclusions that we have drawn about dark matter if it has if it is a sort of a particle in its nature. Okay, so the point being, in the standard model, there is no such particle. Okay, so here I show you the standard model particles just to remind us briefly. We have the quarks, which are colored. We have the leptons, which are not colored, but are electrically charged particles. And then we have basically the gauge bosons and the scalars, which is the Higgs, the W and the Z, the photon and the gluon. Out of all these, the particle which does not couple to photon, which is charge or color neutral, which is pretty much stable, is the neutrino. It comes pretty close to being the dark matter candidate, except the fact that since neutrino is massless or close to being massless, these are relativistic species, and we have said that most of dark matter needs to be non-relativistic. So neutrinos come pretty close to being dark matter, but they don't fit the bill. And therefore, we need to have an extension of standard model in order to accommodate dark matter, in order to find what is this 25% of the universe is made of. So finding dark matter can lead to the next standard model of particle physics. And that's amazingly exciting because it tells you that you have gone an inch closer to finding the theory that makes universe tick. And that's fantastic. So that's what the hype is about. To be able to understand what makes universe tick, right? So within the standard model, as I said, there are gauge bosons and scalar bosons, and these are basically force carriers of the standard model, and also what are called as mediators. Okay, so I would call them standard model mediators, which basically mediate force between standard model particles from one to the other. So you can have a QQ bar pair interacting via photon, which goes to an LL bar. You can have a QQ bar interacting via a Z, which goes to an LL bar, things like that. And also with the Higgs, it basically is a Yukawa interaction force, right? Very good. So the way there are interactions mediated within standard model, you would also want interactions mediated between the standard model and the dark model. Let me call it dark matter or dark model for now. And these two sectors are basically also connected by some kind of a mediator. That's sort of the big particle physics picture we are looking at. Now you can go and interrogate this dark model. What is this dark model made up of? It can be a single particle, okay? And then if it is a single particle, you can say, well, is this single particle stable, unstable? Does it talk to itself? Does it not talk to itself? So stable, unstable, self-interacting, non-self-interacting. Just some of the possibilities of what this dark model could be. Well, you can say, well, the dark sector is not a single particle, but it's an extended particle. It's a collection of particles. And at the moment, nobody stops you from doing that. And again, this extended sector can have several particles, which can have several properties. They could be stable, unstable, self-interacting, non-self-interacting, all kinds of things, right? So you get the idea of how quickly the kind of models of dark matter that you can write down explode and give us several different possibilities. Although, I mean, having said all of this, right, one of the very primary question that we would want to understand in any model of dark matter is how did it originate? How does 25% of dark matter remain in the universe today, right? And that mechanism that generates this amount of dark matter, which is called relic density today, is a very key question to be answered in several models of particle physics of dark matter, okay? So I'm going to slowly explain one of the many ways in which you can explain the origin of dark matter in the couple of slides. Okay. So let's have a thought experiment, right? Let's consider a universe, which is a box of a finite size, and it has a finite temperature. Now we have particles of type A, let's call them red particles, and particles of type B, let's call them green particles, such that the mass of red particles is greater than the B, and they have constant velocities, some V and V, fine. And they are at equilibrium with each other, okay? So we have several cases. First case, that particles don't interact with each other. So the universe will stay the same forever. The box will sit there, nothing will happen. Fine. You can have a case B where interactions of the type A going to B are allowed, but reverse interactions are not possible. So all particles of kind A will convert to particles B, but no particles B will go to particle A. So after a certain time, the universe will deplete all A particles and will only contain B particles. Okay, so that means if A is dark matter, after a while, there is no dark matter in the universe. That doesn't help us much. Then you can have AA, so all particle A can go to B, B can go to A, and nothing else happens. That means the universe maintains equilibrium forever. The A particles, whatever they were at the beginning, stay until the end of the universe the way they are. That means that you have to start with 25% of dark matter. That's a very strange number to start with. So maybe not the best idea. But we do know that the universe expands, and as it expands, it cools down. So again, you have thermal equilibrium. A's are going to B, B's are going to A, and the universe is now cooling down. What happens in this case? So now you can understand that qualitatively, right? You have velocities of the particle as the universe are cooling down. They reduce just by your Boltzmann constant's time temperature, which is approximately the kinetic energy of the particles. You know the rate of the interaction, which is just the cross-section sigma. And you know the relative velocity between particles, which is just, subtraction of the two velocities. So now you do your classical mechanics thing. You have a cross-section, you have the velocity of the particles, which is passing. So you can compute the flux, which is nothing but the cross-section times the velocity. And we also know the number density. So therefore, the characteristic time scale of this whole system is nothing but number density times the cross-section times the relative velocity. And you can see that the unit of this entire calculation is about, is inverse time, which is perfect because the universe is expanding and the expansion also has units of inverse time. So it's perfect. So A is our dark matter, B is our standard model. Now you're having interactions and the interactions are slowing down as inverse of the time. And the universe is also expanding. So what happens at some point of time, this rate, which is slowing down and the expansion of the universe catches each other, which is the number density times cross-section times velocity becomes equivalent to the Hubble expansion of the universe. And at that time, basically the dark matter particles stop interacting with the standard model particles, okay? And that is basically what is called as freeze out. This is one of the very well-known and common mechanisms which explains why dark matter is 5 times more than standard model, or 25% is the relative energy density. And it's kind of nice because it can be conceptually understood. It's mostly thermodynamics that I said to you just now, right? Now, whatever I told you so far is very good conceptually. In reality, if you want to do calculations, you need to consider distributions of particles because, as I said just at the couple of slides back, the dark matter doesn't have a constant velocity, but it has a distribution. So you need to consider basically detailed thermodynamical processes, but essentially the conceptual flow that I have written down here goes through, and roughly speaking, freeze out happens when the rate of interaction between dark matter and standard model becomes equivalent to the rate of expansion of the universe, okay? And this is basically called freeze out. So if you were to do this calculation, now you see that from going from a box, which just has particles inside it, I have slowly introduced to you a concept of Feynman diagram here. So going from, if you write down this entire mathematical formulation, you come across this equation that I have written at the top of the slide, okay? So omega h square here is the density of dark matter that we observe today, the relic density, which is the amount remaining in the universe. And you can obtain this if you have dark matter particle of hundreds of GeV, and if you have weak scale coupling of dark matter with the standard model. And this is rather nice, and this is exactly why it is called as a weakly interacting massive particle, okay? So we are dealing with weak scale physics. We are dealing with things that we know, and this is highly exciting because, okay, we know how to deal with it. We've measured weak scale interactions at colliders and everything. That makes us very happy. Okay, and exactly this is the point where connection between quantum interactions of field theory and cosmology is made, right? Because as I said, I've slowly gone from putting dots in the box to writing Feynman diagram. And that is exactly the place where cosmology kind of meets particle physics in the context of dark matter, okay? So it's the particle physics models that dictate how to generate these cross sections. So from particle physics point of view, you get the cross section and you get the mass of dark matter as an input to the cosmology that you want to explain. This is fantastic. So we have a 100 GeV particle and we have a 0.1 coupling. Let's go search for it. Not quite, because if you could write down one way of making dark matter, you could write down many ways of making dark matter. And if you do that, and theorists have been busy doing that for about 100 years now, you come up with models that has about 63 orders in cross-section and 51 orders in masses. So this gives you a really, really, really big parameter space to look at. And this is one reason why it is so difficult to search for dark matter, and the progress sometimes appears slow. But it's not because we are out of ideas. It's just because the parameter space that we are looking at is humongous, and it takes time to cover it. Okay. So I will basically now give you a couple of examples of what kind of theories we can write down and how to look for them. So I started with this Feynman diagram where you have two dark matter particles that go to two standard model particles. I will only consider a dark model that has one particle in it. So if you go from, you see the diagram here, if you go from left to right, you get a dark matter standard model going to dark matter standard model. That is called as direct detection. And I call it shake it, okay? We call it shake it in our community because you kind of go back and forth. You shake dark matter particles and standard model particles. If you go from bottom to top, you start with standard model particles, you make dark matter particles, and we call it make it. That's a collider production way. If you go from top to bottom, you start with two dark matter particles and you go down to standard model particles. And this is used in indirect detection, and we call it break it. So you can break it, shake it, make it dark matter, and all these three aspects are continuously used in order to understand what dark matter could be. So I will not talk about indirect detection at all. I will just briefly talk about what collider and direct detection searches do. So any direct detection search plot you will see that it has a cross section and it has a mask and it has tons of lines on it. And each of these lines basically comes from a separate experiment. So if nothing else, one thing that you should take home from here is that there are multiple direct detection experiments which are looking for dark matter today. And that gives us a lot of hope for the future that maybe one of this is going to detect a signal some years down the line, okay? Or maybe we already have. So how does it work? It essentially works to first approximation with classical mechanics consideration. You essentially have a system where a detector is stationary, sitting at Earth, a dark matter particle comes and it kicks the nucleus. The nucleus gains a recoil energy and the dark matter particle goes away. And you can compute this recoil energy. And basically you come up with the fact that if you have hundreds of GeV of nucleus, which is typical target mass, you get a recoil energy of about a few hundred keVs. So these are very, very low energy experiments, beautiful stuff to maintain, to look at, to calibrate. And basically such kinds of interactions give you limits on how strongly the incoming particle can interact with the nucleus, right? And that's basically why you get these plots where on one hand you have the dark matter mass and on the other hand you have the cross section. You can look at dark matter at colliders, you can make it. And this is exciting because if you can make it, you have a control over all or many of the properties of dark matter, okay? So here I show you an event from Atlas experiment where this is not quite dark matter event, but this is how a dark matter event will look like. And I'll come to why in a minute. But it's a very spectacular experiment event. What you see here in yellow and green are visible stuff. These are jets, okay, that you see at the LHC. These are quarks when they hadronize. And you see that all the visible particles are in one direction. If you want to conserve momentum, there has to be something in the other direction, and that something is basically called missing energy, okay? So you have, and this is basically stuff going back to back. You see something and the other part of it is missing, and this missing energy can basically be your dark matter particle. Because it's charge neutral, it doesn't interact in the collider. So this is basically a classic way of making dark matter at colliders. And exactly this is what I show you on this slide. On the first box here, you see the same search where you have two dark matter particles. You see a Feynman diagram, QQ bar, going to chi bar. The chi is dark matter. And then basically you have the jet in the initial state. And when you look at the collider, you only see the jet, you see nothing else, and it's called as a monojet event for no, it's an obvious reason. So you can make this dark matter particle and you look for it in monojet. You can also look for a particle that mediates the interaction between standard model and dark sector, which is mediator particle. And this is called as a resonance search. And one of the classic examples that you all should be familiar with is the discovery of Higgs boson, because we exactly looked or observed the Higgs boson by observing a resonance that sits at almost 125 GeV. Okay, so we have done it before, and if there exists another particle which can create this resonance, we should be able to see it. Well, dark matter could be a part of extended sector, and supersymmetry is one of such possibility. And if that is the case, then you can look for production of these extended sector particles. And this is basically what you see on the last box on the slide, where you make heavier particles, the heavier particles decay to dark matter, and then you search for such kinds of additional processes at the detector. And all of this, which is direct search for new physics, is complemented by indirect measurements. Basically, you want to know what you don't know by measuring everything that you know to highest precision possible. That's basically the point of the story. So for example, if the Z boson couples to dark matter, then you should be able to, you measure all the properties of Z boson very, very well. So you know if Z boson has a possibility of decaying to dark matter or not. Same goes with the Higgs. And then you can also have, for example, new particles which circulate in the loop and goes in the direction of flavor physics. So this is indirect search program, and both of these are extremely important to constrain the nature of dark matter. So I'll just give you a couple of examples, and somebody should tell me if I'm running over time at some point, okay? So here you have, let's take the simplest possibility. We know standard model. We know the standard model Higgs and the Z exist. But if they maintain or if they mediate forces within standard model, why can't they mediate forces to the dark sector? So let's say that the Higgs talks to the dark matter particle or the Z talks to the dark matter particle. Well, can we look for these and what kind of possibilities exist in these scenarios? So indeed, people consider these models to a huge extent. And now I will show you a few plots that help us draw very nice conclusions about standard model processes that can mediate interactions to dark matter particle, okay? So the first part is when the Z boson talks to the dark matter particle with a gauge strength, just like in the standard model. So what you see here is a plot that has the direct detection cross-section, how strongly the dark matter talks to nucleus versus the mass of this dark matter particle. The line on this plot is exactly the point where the relic density is generated, where you get 25% of the universe making up dark matter. The shaded region with mass less than 45 GeV is excluded because we've measured very, very, very precisely the invisible width of the Z boson from LEPPARS, which is coming, with the experiment which ran from 1989 to 2000. And this basically excludes this region, which is less than 45 GeV. For anything more than 45 GeV, direct detection cross-section is so low that it excludes all the region that can basically create relic density of dark matter. So that basically tells you that dark matter cannot couple to the Z boson with the full weak force interaction. And this is a very, very strong statement that comes because you've considered all possible experimental searches and what do they tell you about the underlying particle physics model. You can play the same game with Higgs. Here, instead of showing the direct detection cross-section, I've shown the coupling, but it doesn't matter. It's very equivalent to each other. And again, in this plot, you have the line that generates the relic density. If you sit on this line, you create 25% of the universe containing dark matter. Then you have the blue region, which is excluded by direct detection experiments. And then you have the brownish region, which is excluded because you have some idea of how many times Higgs can decay to invisible particles in the final state, okay? And the dotted lines that you see, the black dotted lines, are the future. And in fact, one of the main aims of future collider programs is to measure the properties of these Higgs particles so that one of the things you achieve is whether the Higgs talks to the dark matter or not. And this is pretty exciting because the way you've drawn conclusion about the Z, if you can draw a conclusion about also Higgs, then you know there has to be a completely different mechanism that mediates dark force or dark matter interactions to the standard model interactions, okay? You can do the same story with supersymmetry. And here, the story gets a little bit more complicated. So I will not introduce supersymmetry to you, but basically show you how different constraints basically constrain this dark matter parameter space. So in fact, this was one of the works that we did with Rohini, and this was very, very exciting when we did it, because for the first time, we were showing that very light dark matter up to 15 GeV or so was allowed. And at the time, it was not known that such a light particle can exist, right? I mean, people had it was not very clear how light dark matter particle can be, and we kind of came and showed that it can be very, very light. So here what you see is the Sion region is what is allowed if you take the Lep physics, the Z invisible measurements, and so on and so forth. Out of which you see a lot of region gets excluded if you put the Higgs measurements. So we've looked for Higgs, we have measured a lot of couplings, and if you put those constraints, you get this blue region, which is allowed. And on top of that, if you say, well, I know that direct detection exists, I know that relic density has to be made, I know that LHC searches for supersymmetry needs to be satisfied. And if you apply all those constraints, you get this orange or red region. So it tells you that application of several different constraints, one after the other, chips away a lot of parameter space from supersymmetric dark matter scenarios. Of course, as I said, everything that I have said so far comes with its own caveats. So you could have alternative scenarios, but at least within a specific model that we considered, slowly, the combination of experimental constraints on theory space, both from astrophysics or direct detection and LHC searches, is constraining the space of supersymmetric parameters. I'll give you one more wild example where I will connect astrophysics with relic density, with density distribution of dark matter, okay? So here, I said here at the beginning of the talk that the density distribution as predicted by simulations is not quite the reality. And here on this plot, you see that the dashed line I have circled are basically the predictions of the simulations, and the dots that I am showing again circled is basically coming from observation. And such kinds of observations can be explained if dark matter interacts with each other with very light mediators. These are called Sommerfeld enhancements. And such self-interactions bring the observations closer to the theory prediction. Okay, so this is very nice because this is self-interactions, this is completely new, and this explains some of the observations. So it's very, very exciting. The same mediator talks to the nucleus and can generate direct detection interactions, okay? So you can plot the allowed parameter space from self-interactions and the possibility from direct detection experiments. And you see that direct detection experiments can in principle be sensitive to self-interaction cross-sections that happens at the center of the galaxies. And this is pretty wild when you think about it, because you're talking about an experiment sitting at the Earth, thinking about or pointing towards something that happens at the center of the galaxies. This is something which is very, very exciting for me. So direct detection experiments can tell us something about the dark matter interactions at the center of galaxies, okay? So this is basically where some of the examples where you can think about dark matter, what it can do, and we've sort of, seen a few things and understood a few ideas. And it seems so far we've not found anything. So where do we go from here? There are a lot of exciting things happening in dark matter today. And I only highlight very few. This is personal bias. These are personal choices, okay? One thing which is very nice is people are thinking about what happens if dark matter is very light. How does it interact with the detector? And it may not interact with the nucleus, but it can interact with the electron, and it can do all sorts of fancy things. And it has a good overlap with material science. So, there's a lot of community which talks to material science, solid state physics, those kinds of things. So from both from theory and experimental frontier, this is a highly exciting field. You can say, well, you've talked about dark matter being a single particle, and you've not found it so far. Maybe dark matter is not a single particle. It's QCD-like interactions, and it probably strongly interacts with itself. This is possible. This is also a very new idea on the market. And if that happens, then phenomenology at the LHC can get modified significantly. And these strongly interacting dark matter scenarios are also highly exciting, which are just now being studied. I talked about 2-to-2 interactions. I talk about 2 dark matter particles going to 2 standard model particles. But you can think about particle physics models where 3 dark matter particles go to 2 dark matter particles. In other words, dark matter eats itself up. And if that happens, you have completely different ways of generating relic density, completely different ways of doing self-interactions, and again, a very different kind of parameter space to play with. And then all of these is complemented by the upcoming astrophysical surveys, which will basically look at movements of stars, which will look at substructures of galaxies, and which will look at universe in more and more details to tell us how dark matter behaves, not at the biggest scales, but also at smaller and smaller scales. So what will those tell you? And will they tell you that we are missing something important in the picture of dark matter? It's yet to be seen, but so I think it's fair to say that it's highly exciting that there's so many nice ideas out there and still needs to be explored in detail. So I will basically sort of end with a very nice quote from Vera Rubin, who was one of the first people who actually showed the rotational curves of galaxies having discrepancies. She says, don't shoot for the stars. We already know what's in there. Shoot for the space in between, because that's where the real mystery lies. Okay, very well. So that's basically all I wanted to say about what dark matter could be, how we can look at it, and what we have learned, at least a little bit, give you a taste of it. And as Mishra ma'am said, I have a project which is basically taking this strongly interacting dark matter scenarios and connecting them with the experimental signatures at Large Hadron Collider. So how does the theory space talk to the experimental space, and what the experimentalists have done so far is the aim of the project. First, you must be interested in numerical simulations. This is not an analytical project. You need to have an access to computer and an internet connection. And you should know field theory or standard model, at least be able to compute Feynman diagrams so that you can do some calculations on your own. It will be very nice if you have some previous knowledge of programming in, say, Python or C++. If you don't, you at least should have a very strong desire to learn it. Okay, so that's basically all I had to say. And I leave you here with a bunch of literature on dark matter. You can go read it. Many of these are extremely nice lecture notes. I can send around the slides so you have access to it. Thank you very much.
Thank you, Suchita, for a very informative and very scintillating talk. The talk is now open for questions. You can unmute yourself and ask the question.
Hi, can you hear me?
Yes.
Hi, this is Tamasi. Hi, Suchita.
Hi.
Thanks for the very nice talk. I would like to go to page 22, where you showed this nice distribution of Dijkgem masses. Yes. So here you also related when explaining to the Higgs resonance searches. So for when searching for the Higgs resonance, we kind of knew a mass region where we were looking at. What about dark matter particles? When you spoke about the mass ranges, you also mentioned about MeV scales, but you also showed some TeV scales. So
exactly, yes. So that's the fun part of the story, right? Is because I showed you dark matter or models of dark matter, these WIMP dark matter scenarios, which have hundreds of GeV of dark matter particles. Okay, so if the mass of the dark matter particles is hundreds of GeV, it's natural to expect that the mediator also has hundreds of GeV scales, roughly speaking. So that gives you one expectation about what this scale could be. And then you look at LHC, you look at hundreds of GeV, TeV scale resonances to see if you find something there. But I also said at the end of towards the end of the talk, that if you have very light mediators, so I was talking essentially here, if you have these very light mediators, they give you Sommerfeld enhancements, and these help you to solve the discrepancy between observed density distribution of dark matter versus the simulated density distribution of dark matter. That tells you that the mediator can also be very light. That gives you MEV scale mediator scenarios, okay? And at this moment, a priori, there is little expectation as to where this mediator can be. If you want to basically explain dark matter, or you want a dark matter to explain the density distribution discrepancy, you better look for very light mediators. If you say, well, this discrepancy is not because of dark matter, but some astrophysics which I don't understand, then again, you can look for all kinds of mediator masses. It really doesn't matter at that level, or you don't have a first principles expectation as to where these mediator masses in terms of resonance searches could be. And that's what makes this game exciting and frustrating at the same time, because there are too many ideas and you want to look for everything.
So far, none of the mass range is excluded yet? Or you mentioned 45?
Yes, so I probably won't have a slide for you for that. Unfortunately not. Let me just, give me a second. Let me pull up. So we do have a lot of resonance searches which are currently ongoing, okay? And so I can show you one possible plot. Okay, so you see here, this plot basically shows you the mass of a mediator particle Z prime versus some coupling. Don't worry about what that coupling is, okay? This could be the same coupling to dark matter particle. What is important is it shows that you have resonance searches which are at LHC, which go from about 10 GeV all the way up to a few TeV. Okay, so this is your dilepton search, so pair of leptons in the final state. This is also a dilepton search, so again leptons in the final state. And then you have this gray region here, which are searches coming from basically fixed target experiments, Bell, low energy colliders, and things like that. So you do have a lot of constraints on the coupling mediator to the standard model particle, but you don't have a very good understanding of the coupling of the mediator to dark matter. So you can always tune one coupling to the other and make these scenarios possible. That's the point of the story. So that's why these are allowed. It's not that we have not looked for them, but it's because there is a degree of freedom in the whole process that is still, that makes these scenarios still viable. Make sense?
Yeah, thank you.
There's a question from Rishabh Gala. Rishabh, you can unmute yourself and ask. Or should I?
Hi.
Hi.
In slide 5 or I think 11, you said that dark matter is mostly non-relativistic. So do you have any observable evidence to believe it was relativistic in the early universe?
Very good question. So, right. Right. So in fact, and in the early universe, because the temperature of the universe was high, you see, as the universe cooled down, right, as we were doing our thought experiment here, we said that basically the temperature of the universe is related to the velocity of the particles, so to say. Yeah. So as the temperature goes up, the velocity goes up.
Yeah.
Okay, as the temperature cools down, the particles start to become more and more non-relativistic. So if this picture is correct, then probably earlier in the universe, dark matter particles had high enough velocity.
Yes. Okay.
Okay, there's a question on YouTube from Akhilesh Tade. He's asking, can you please explain why dark matter interacts weakly?
Oh, okay. Very nice question. Okay, so basically, the reason why we expect dark matter interacts weakly with the standard model is because, is for a few reasons, okay? One thing is if it was to interact strongly, which is like QCD, then it would have actually messed up a lot of standard model. Okay, because it would have made difference to how the atoms are formed or how the nuclei are formed. These constraints come from measurements of proportions of atoms and nuclei very early in the universe. This is called Big Bang nucleosynthesis. And it's incredible that we've been able to measure these things. And these tell you that the formation of nuclei and atoms in the universe formed or can be very well understood within standard model. So you don't want to have additional strong interaction that destroys it. Then you can go and look at experiments. And this is what I was trying to say or show here. Basically, the experiments in the early days started to probe cross-sections which were quite large. And as the days go by, they are probing smaller and smaller cross-sections. So at this point of time, because the experiments have progressively probed smaller and smaller and smaller cross-sections, we know that the interactions between dark matter and standard model, which kick also the nucleus, are also weaker and weaker.
Thank you for the answer. I have another question. So if dark matter is like QCD, what kind of symmetries or like degrees of freedom are like should we look at?
Right.
Like what kind of questions should we ask?
Yeah, so this is an absolutely interesting question, right? Because if dark matter is like QCD, then the game becomes very different. And it becomes different for the following reason. See, you're basically looking at non-abelian theories once you start to talk about strong interactions, once you start to talk about QCD-like sectors. And then the question is, okay, you want to have non-abelian theories and you want to choose a specific gauge symmetry and representations, okay? This becomes a game of group theory. And as you know, there are multiple groups out there available, okay? So there are basically SOs, there are SUs, so there are symplectic and abelians and so on and so forth. So basically, you can write down dark matter theory in every of this group. You can say SUN theories, you can take SON theories, you can take SP theories, and each of these theories in each of these gauge groups will give you a different kind of dark matter phenomenology. Again, a priori, there is not necessarily a specific direction you can go into. So you want to actually investigate going from one gauge group to the other very systematically what kind of dark matter phenomenology comes out of it. So there is no good answer to this question. You just have to do your homework and chip through this parameter space of group theories and representations and confront each of these with the experimental constraints. That's the game right now.
Thank you. Yeah. What like are you looking for? Are you like applying or formulating using like a particular gauge theory, a particular group for this?
Yeah, okay, so that's also a very nice question. So, right, so in my particular personal research, I'm interested in both the SUN theories, which are like standard model QCD, maybe with a larger gauge group, but also symplectic theories, so SP gauge groups. I have not yet thought so much about the SO gauge groups, which have their own phenomenology and own kind of parameter space. But these are kind of the two gauge groups that I'm currently very interested in.
Okay, thank you. Thanks a lot.
There is a question by Garima Verma. Would you like to speak yourself, Garima?
Yeah, hello, ma'am.
Hi.
Hi, really nice lecture. I really loved your lecture.
Thank you.
Yeah, so my question is that you said that in the early universe, maybe the dark matter was relativistic.
Mm-hmm.
Yeah, so how could that, so at that time, wouldn't be the time be, how could you say that the time be linear at that point?
I'm not sure how I understand the question, because the linearity of, I mean, dark matter being relativistic, meaning moving with higher velocities.
Yes,
why would it affect time?
Yes, ma'am, as the time could have slowed down, or it have maybe reversed if that has been a relativistic point of time.
I think what she's asking is if you can use the non-relativistic definition of velocity if the system was relativistic. The concept of velocity.
I see,
yes.
I see. Oh, I understood. I think, okay, I conceptually tried to explain how you can think that dark matter was relativistic at an earlier stage in the universe. Of course, I mean, you can't use the non-relativistic formulation, which is just half mv square. At that time, you have to take into account full relativistic formulae, but I was trying to explain it conceptually for why one would expect that dark matter had higher and higher velocities earlier in the universe.
Oh, thanks, ma'am.
Sorry about that.
So one last question by Akhil Maru. Okay, there are two more questions. Akhil Maru, would you like to speak? Or I'll just read out. The power spectrum of the CMB shows the evidence of presence of some structures formed in the early universe before the CMB itself, as far as I have studied. It might as well be dark matter. This is comment. It's in the chat box, Suchita.
Yes, I'm trying. I have a chat box open on one side, so I'm trying to look at the question as well. The power spectrum. So I, off the top of my head, I cannot think about a straightforward answer to this question, right? I mean, sure that the most of the power spectrum of the CMB can be explained with the ingredient of dark matter, right? That we see. In fact, the power spectrum itself is one of the best evidences of dark matter we have, because it's the ratio of the first peak to the second peak. Now, the earlier structures formed in the universe before CMB, what they were and how they came to be is a highly speculative regime at this point. And in fact, we do have experiments which are going on, which sort of try to probe that region before CMB. But at this moment, I'm sorry that I don't have a more straightforward answer to your question. So I'm sorry for that.
Ravi Singh?
Yes, I wanted to ask, would it be possible that dark matter is not real and dark energy is a real phenomena, and the expansion of the space between the galaxies from all sides keeps those galaxies intact? Instead of some particle keeping the galaxies together, maybe the dark energy is not allowing them to break apart.
Okay, so the thing about dark matter is that it doesn't exist only at the scale of galaxies. Okay, it exists, as I showed you at the beginning, it exists at the scale of galaxies, at the scale of clusters, at the scale of universe. So in fact, people tried to explain the behavior of galactic rotational curves by introducing local phenomena. And they said, okay, you could fit to the rotational curves of the galaxy, no need of dark matter, is everything good? But it becomes increasingly difficult, although probably not impossible, if you want to take the same phenomena and explain observations at cluster, observations at the scale of the universe, and so on and so forth. So you don't want to explain just one observation. And that's the beauty of, the evidence of dark matter that we have today, is that it goes from the scale of the galaxy to the scale of the observational universe. And all these things are consistent with each other. So if you want to have an alternative theory, which doesn't need dark matter, then you should have it such that it explains all these evidences in one go. And if that can be written down, why not? Probably we don't need dark matter, and that's perfectly fine. So answer to your question, if you do write down such a model, you should go and check if you can explain CMB.
Sure. Thank you.
Next, Aksa.
Yeah. Hello.
Hi.
Yeah, hi. Thank you for the great lecture. I really enjoyed it. So I'm just beginning to study about neutrino physics, and there's this existence of sterile neutrino which can be added to standard model in order to explain the existence of dark matter. Can you elaborate a bit about that? Like, what is the possibility, and are we looking into that rather than going out of standard model? And
yeah, okay. So very nice question. Yes, sterile neutrinos, which are basically fourth neutrino species, can be considered as dark matter particles when they are very light, okay? And this is very, very exciting. This is something people have been looking at for many years now. So this is also under high scrutiny, so to say. And some of the constraints on that parameter space comes from what is called as neutrino oscillations, okay? Which is neutrinos, when they travel in space, they convert from one flavor to another.
Yep.
And we can measure these oscillations very, very, very precisely, not as precisely as we want, but still to a good accuracy. And these oscillations put constraint on the existence of fourth neutrino, okay? Just like the Z decay puts a constraint on the dark matter particles decaying possibility, the oscillations put constraint on the fourth neutrino that can exist. Then there are additional constraints which are coming from astrophysical observations. So you can go and look at this fourth species from several different astrophysical constraints, and that again puts very severe constraint on the parameter space. So probably there's still some bits which are still allowed, but it has started to become increasingly difficult to say that sterile neutrino dark matter is a good candidate. It's probably still allowed in a very small region.
I see. Yeah. Thank you.
Welcome.
Radhika.
Okay, thank you for a good talk. You mentioned about Z boson couplings with dark matter, and in that you mentioned that dark matter cannot couple to Z boson with full weak force. So what are the other possibilities of coupling? And second question is, I recently read about long-lived particles, so LLPs. So can means in order that they become a dark matter candidate or dark matter particle, what are the constraints?
Okay, so both great questions. With the Z boson, right? What you know is that the Z boson couples to the left-handed particles in the standard model. So what you can do is you can introduce a right-handed component, which basically reduces the coupling to the standard model. Okay, the more the right-handed component in your dark matter, the less the coupling to the Z boson. And then you can basically start to chip away. You're basically reducing the coupling of dark matter to the Z boson. And once you reduce it enough, you're still okay to couple a dark matter particle to the Z boson in the standard model. In fact, you do that in supersymmetry. Some of the supersymmetric particles do couple to the Z boson, but not with the full force, full weak force. They have a right-handed component, so they have a chirality interactions there. Your second question was concerning long-lived particles, right? So as I said, at the beginning of the talk, for one possibility is dark matter itself is a long-lived particle, okay? The only constraint that we have, so to say, is that the age or the lifetime of this dark matter should be much longer than the scale or age of the universe. So long as you fulfill this, you can in fact write down an unstable neutral dark matter particle as a particle in the BSM theory to be a dark matter candidate, and everything is good. There's no problem with that. Now you can say probably some kind of long-lived particle mediates interaction between standard model and the dark sector. These kinds of theories are also being studied by a lot of people actually currently. This is a very, very exciting field. And sometimes it's possible to detect these long-lived particles, which are kind of the responsible particles for generating relic density at LHC. But many times it's possible that these long-lived particles interact so weakly with standard model that probably our colliders have no chance of detecting them. So yes, there is a very intricate connection actually between relic density generation mechanisms, which are not WIMP-like at all, what I'm showing on the screen here, which are completely different relic density mechanisms, and they go into the parameter space of long-lived particles.
Thank you.
Srishti Sharma wants to ask something.
Good evening, ma'am.
Hi.
I have two questions. The first one, I realize it might be a long stretch, but in inflationary theory, we've read about the quantum fluctuations. Quantum fluctuations giving rise to large-scale structures, and a strong evidence of dark matter has been observed around like dark matter halo, which is observed due to galaxy spins. Can these two things be interconnected somehow? That the quantum fluctuations which gave rise to large-scale structures like galaxies, can they also be a can we connect dark matter to?
Yeah, okay. So this is also a very nice question, right? Because what you can do is, so again, on the slide, I've shown that dark matter talks to standard model. And you can ask a question, why should dark matter talk to standard model? I can generate the dark matter density with some 3-to-2 interactions or some self-interacting dark matter or some funny mechanism. Why should dark matter talk to standard model? Probably there exist theories out there where there is no interaction between dark matter and standard model. And in this case, the only way you can detect these particles is by looking at gravitational interactions. So how do you generate such particles? One way of generating them is by decaying an inflationary potential. Okay, so there exist theories out there which in fact do connect inflation with dark matter particles, in the sense that the particle which is responsible for inflation probably also is responsible for generating dark matter particle. So these theories are not completely out of the picture. A lot of people do work on it, and it's a possibility, yes.
Thank you, ma'am. And also, as an undergraduate, I am in second year BSc right now. So, what projects would be appropriate for me to get involved in the basics of astrophysics at this stage? Astrophysics as well as particle physics, because I'm really unsure what I want to pursue in the future. So, anything that will help me to, and where can I look for such projects and opportunities?
Right. Okay. So you are at a similar stage where I was when I was of your age, probably, where I was also interested in astrophysics and particle physics and what have you. The one thing that is very, very important is get your basics straight. Study the basic topics and understand very fundamental things, not just in particle physics and quantum mechanics and astrophysics, but also in thermodynamics, statistical mechanics, and all these things. Because as I showed you in the talk, when I was explaining the cooling of the universe and generating the relic density, I used a lot of statistical mechanics in the background, okay? So you need to understand those quantities very, very well to be able to apply them at different problems. So I would say, rather than thinking about specific topics and areas and what you would want to do, please do get your basics straight. Please understand the fundamentals of everything that you're studying. Turn the problem around on its head. Try to introduce new parameters in the things that you are studying and see how things change. And that will give you tools and ideas and appetite for doing research, which is more important than knowing what dark matter could be, in the sense of, studying very tiny, minute theory of dark matter. So that's basically, that would be my advice in terms of what you should be doing. For the projects, there are a lot of opportunities in India, right? There are summer schools that I was talking about. And I do remember attending one of the summer schools when I was still in my final year of undergraduate. So this was fantastic. You do get these opportunities. Go talk to people, ask them questions, after some thinking about what could or could not be a good question. Not 2 + 2 = 4 is not a good question necessarily. But all these questions that I'm getting today, fantastic questions, they're great and they should be asked. So ask questions, make contacts with people, and at the same time, get your basics straight. So that would be my advice.
Okay, thanks a lot, ma'am. Can we get your email address or something where we can get in touch if we have any queries in the future regarding the subject or the project which you are involved in right now?
Connected?
So
yeah.
Should I tell them to send a mail at Gyan email ID, and whoever wishes to have the email ID of Dr. Kulkarni, we will send it to her. Is that okay?
Sounds good.
Or would you like to share it?
Yeah, it's perfectly fine.
Right. So anybody who is interested, if you have more questions, you have questions about the project, please send an email either to me or if you don't have my email ID, at the Gyan email address, and we'll respond to you. And so I will request the rest of the people. There are too many questions. It's a very interesting subject, and there's a lot of interest among the students. And everything cannot be answered right now. So we will request the rest of the students to address their questions to Dr. Kulkarni in email. And I would like to now, the email ID has been written in the chat box. It is gyan.udp@physics.mu.ac.in, for those who are not aware. With that, we come to the conclusion of today's session. And I would